All right, we're going live on streaming. Let me go ahead and post this link so that people can help us get this posted in case anybody wants to join on YouTube. 1 second. This is looking good. Hi, everybody out there in YouTube land. If you're there, see we have a number of viewers. I just need to get this link out to the world at large, and then we're going to dive in. Okay. Excuse me. So I hope everybody can see okay. All right. This is the ClickHouse community meetup. Let me go ahead and start some more recordings. We're going to be recording this 3 ways. So we're going to go ahead and resume Zoom recording. All right, great. So Zoom's got the recording. Let me go ahead and start my favorite way of recording, which is OBS Studio. I just love this software. It is the best. So we'll go ahead and start OBS Studio. And that way we can't possibly lose any of the great stuff that's going on here. Okay, so welcome everybody to the ClickHouse community meetup for February. Let's go ahead and check the number of participants. What we'd like to do is give people a quick chance to say hello if they would like to. The early ones, anybody who's late, they have to do it later. So I'm going to go ahead and just unmute people. Anybody? Hey, Jeff, how's it going? If you want to step up and just say who you are, what you're doing with ClickHouse, go for it. And for those of you out in YouTube land, feel free to put in a comment. Just tell us what you're doing, and we can also share that.
Hello, my name is Timur. I work as a lead DBA in Five9 company. We use ClickHouse for internal analytics.
All right, welcome, Timur. Anybody else want to do an intro?
Hi, my name is Naveen Sukumar. I work with Frank at Materialized. Just here to listen along. And of course, Robert, we met at reInvent. So good to see you again.
Excellent. Yeah, great to see you. Other folks want to jump in? So don't be shy. We'll do a few more. Otherwise, if there's nobody else that wants to jump in and introduce themselves, feel free to do so later on. This is pretty interactive. We're going to dive in and get started. So you have joined the February SF Bay Area ClickHouse meetup. It used to be in person. That was back before we had pandemics. Nowadays, it's online and really worldwide. We have people coming from all over the planet tonight. So we have a great agenda. I'll talk about that in a second, but I just want to announce a couple of events coming up. So on February 17th, we have the ClickHouse 22.2 release webinar. I think if you're a ClickHouse user, you definitely don't want to miss that. There's just a raft of cool features coming out. Alexey will give the full year plan, but that's no doubt going to have some really great stuff. Sign up link is here. I'll post it in the chat in a minute so that you can get to it easily. Our next SF Bay Area meetup is scheduled tentatively for April 20th. I haven't published it yet. We've got one more or less confirmed talk on Apache Pulsar. If you remember, either last time or the time before, we had Red Panda. So we're kind of making the rounds, talking about event streams, let people talk about how to use them and integrate with ClickHouse. We have room for a couple more talks. Please step up and do something because it gets really boring if I have to do more talks. We want people in the community to do that. So speaking about me and who's sponsoring this, we are Altinity. I'm the CEO, is my day job, but I'm basically a database geek like pretty much everybody else on this call. And Altinity works on ClickHouse. We have a bunch of customers. We run a cloud service, help people use ClickHouse effectively, and we love databases. We are also hiring. So like probably most companies on this call. With that, I'm going to just get out of the way here. I'd like to go ahead and introduce our first speaker. I am really happy to introduce Frank McSherry. He's Chief Scientist in Materialized, and he'll tell you all about what Materialized is, but they basically do materialized views, and it's kind of like a database down there. We love materialized views in ClickHouse, so I thought it would be really cool to invite Frank and the Materialized team to talk about what they're doing so we can see what the neighbors are up to. And so with that, Frank, I'm going to stop my share and let you take over.
Well, thank you very much. Let me see if I can share this thing up here.
You are fully shared. Take it away.
Wonderful. All right. So I'm going to be talking, about Materialize. This is a thing we're working on over at the company Materialize, and it's a platform database, if you will, but a platform for changing data, working with data that are continually changing. And the gist of the talk is to walk through how we contend that you can totally use something like SQL. It's often your favorite query language, but SQL, a nice declarative language for building scalable streaming infrastructure. So you can, all the use cases you might have had to pull some streaming system off of the shelf. We're going to try to claim that you can get there just by writing some SQL stuff. And well, I'll talk you through the parts of it, especially if you're, if SQL is not a thing you're into, or potentially streaming systems. We're going to talk through each of those things too. All right, the structure of the talk. There's three parts, and I'm going to be totally honest. I think we're going to get through the first part. The second part is pretty cool, and it's talking about some work we've got upcoming in Materialize to make it more sort of cloud native and scalable in the cloud. But to be totally honest, I think part one is probably about as far as we're going to get, and that's fine. I'm happy to chat with anyone about part two offline. And because we might not get to it, part three, I just want to call out here, Materialize is a great place to work. We're doing lots of really neat things, and if any of you are, this resonates particularly well, get in touch. We'd be delighted to chat with you. But I'm going to start out with part one, which is essentially a walkthrough of Materialize, and the thesis here, which is that SQL and streams work great together. And we're going to get there not just by bolting the two of them together, but sort of from some first principles to try to see what does a database look like if you built it around continually changing data. All right, so we're going to start. The gist here is that I'm going to claim, I think somewhat boldly, that you can write SQL and make streaming infrastructure out of it. And by the end of the section, you'll either be able to believe or not believe that, but at least you'll understand what I'm talking about. So I'm going to start with just a little bit of a history on SQL systems. Possibly everyone already knows all this, but I do want to sort of position us relative to other parts. Like there'll be Materialize relative to OLAP style systems, which sort of ClickHouse is. I don't know. I sort of think of it that way, but I'm probably wrong. So feel free to leap in at any point and say no. But this will put us on the same page at least about relative strengths and weaknesses of different approaches to doing things. All right. I'll make this quick. There's some pictures. If we go back 40, 50 years in time, we have the venerable online transaction processor, which is a great place to store your data, your valuable business critical data. You write stuff into there, you can read stuff back, there are transactions, and it's a good way to sort of keep your data safe. You write your data down and you can look at it again. Pretty popular thing to do. People like that. They're pretty successful, it turns out. But you do other things with databases too. People realize these are great for running analytics, driving dashboards, or feeding various bits of monitoring that you want to do. And at the time, what happens is this really heats up the transaction processor. You might have gotten your database to handle a certain amount of customer load, business load, stuff that you're actually doing. How often do customers change their address? Well, your database can keep up with that. But if you want to keep sort of up to the second fresh statistics about the current efficacy of your marketing campaigns or something, that's a lot more work that's now being targeted at your transaction processing database, not really built to do that. So transaction processor heats up, people realize this isn't going to work, we need to do something different. And the approach that folks came up with, which is a great approach, is to realize that these two different types of tasks are fundamentally different, and you might want different techniques for solving them. So they sort of introduced the online analytic processor, where the difference between these two things, so it cools down the transaction processor, not just because it's another computer. Having two computers instead of one would be great, but really because there are different designs to data processing here. the transaction processors are often row-based because for transactions, that's how you get in and out really quick and do the changes you need to make. Whereas a lot of the analytic processors are columnar and sort of aggressively compressed all of the columns so that you can grind through the relevant subset of data as fast as possible, the highest throughput as possible. And this is great. A lot of the analytics dashboard monitoring use cases were very well served by the analytic processor. They're, the loads that they can tolerate go up by multiple orders of magnitude. This is great. People are asking a lot more questions, it turns out. And actually, that's sort of the problem. Doesn't stop people from being interested in just asking more questions. They just keep asking lots and lots of stuff over and over again. Those dashboards that used to refresh once a minute, you're now trying to refresh faster than that. And it's just lots of work to do here. So although we've made things a little faster, we haven't fundamentally changed anything yet. You've gotten a constant factor, big constant factor improvement. But yeah. What we're going to talk about in this talk is a slightly different change you might make. Instead of going from rows to columns, we're going to think about a different sort of pivot where we're going to think of, there's this term, no one uses this, but we had to make up something, the online view maintenance engines. So rather than thinking about transaction processing or analytic processing, we're going to think about building a system that maintains views over data, where the architectural change is not rows versus columns, but is pull versus push in terms of the execution model. So the OLTP engines and the OLAP engines are pull in the sense that they sort of hang out and they wait for you to ask a question. And when you ask a question, they leap into action and they do a really good job of getting in and out with the answer as quickly as possible. These push-based systems are going to be a little different. At least their primary intent is that you ask questions of them and they give you answers, of course, but they sort of hang out at that point and say, that answer might change. I will leap into action as soon as I hear about the slightest change in the data, and I will tell you about any changes to your queries as soon as I hear about this. If you want to ask the same question over and over again, you're welcome to. It's going to be exactly the same until I tell you about a change to the answer. So it's a different approach to building sorts of systems that works really well for repeated queries that you want to keep fresh, right? Instead of redoing the work over and over again. You basically set up a contract with the system to say, you will tell me when things change, and the system can do some pretty cool things if that's how you set things up. What's an example of an OLVM style system? One we're going to use is Materialized here. I'm not actually aware of that many others. There's some research prototypes out there, and there's some other systems that are sort of starting to creep in the same direction, but haven't really put a stake in the ground as far as like, we are going to be a SQL database that is optimized for reacting to changes rather than regrinding over the data from scratch. So with that in mind, so this is some context. This is up to the current state of affairs. This is why I'm going to be talking about Materialized, is to try to tell you about this, I think, cool new space in the space of trade-offs, basically, in terms of how you might spend your computer cycles and money. So Materialized, how does it fit in? I had a picture of an OLTP source of truth just upstream, but you can connect it to a bunch of other stuff if you like. You have the Pulsar folks showing up. Red Panda is another good example. Kafka is sort of the archetype here, where folks can drop data into a message bus, either from a database into Kafka using something like, say, Debezium, or we can actually pull directly from Postgres replication logs, and having consumed the data, serve up all of the nice analytics dashboards, monitoring use cases, just as if we were a standard database. So if you connected using pSQL or something like that, you just type SQL queries and press enter and get answers. But as you'll be able to see, we're also going to be able to dump stuff back out into Kafka as well, sort of connect end to end with the event-driven architectures that a bunch of people are interested in. Also, I think pretty cool. So with that in mind, what I'd like to do is sort of talk you through some of the look and feel of Materialized. Let's start talking about how Materialized looks using using SQL as a basis for this. And I'm going to try to claim that we can get at a bunch of interesting stream processing idioms just using SQL. So you can just sort of keep your SQL comfort level, such as it is, and get access to a whole bunch of new functionality that you wouldn't have had short of reaching for a custom stream processing toolkit previously. All right, so just to make sure everyone's on the same page about SQL, here's a real quick intro to SQL. So SQL is this structured query language, and the idea is it's ways to talk about data where you can describe various collections of data. Here, tables. Tables have names, they've got fields in them, and there are some relationships between the fields. Here's some sensors, and we've got some readings, and every reading has a sensor that it refers to. And you can sort of see there's some other random fields that I put in there to make the queries interesting. But fundamentally, there's two piles of data here, and you can insert things into the piles of data. You can delete things out of them. But importantly, from our point of view, you can ask questions about these piles of data. So we can do select star from sensors. That just reports out everything that's in sensors. That's pretty easy. But you can write more interesting queries too. And at the very bottom, there's an example of a SQL query that pulls out for each region the maximum temperature in that region. And it's a bit non-trivial because the temperatures are in the readings and the regions are in the sensors, and we got to join the two of them together and then do an aggregation afterwards. And it's, this isn't fundamentally hard. Databases do this a lot, but it's not just looking at the pile of data that you're holding onto. There's some actual work to go on here, and potentially a little bit of non-obvious work if either of the inputs change. But this is SQL, or at least this is SQL to the extent that we're going to work with it in this talk. Now I'm going to make a few claims in two directions. Basically, that SQL and streams get along really well. I want to first claim that SQL and folks who like using SQL style systems actually benefit a fair bit from streams and ideas from stream processing. And if we're lucky, I might be able to connect this back to ClickHouse, which I think of myself as a bit of a stream processor. Though not everyone who uses it thinks of it that way, but I think the same sorts of connections make a lot of sense there, and we'll see if people buy it. So here's one example. SQL systems, absolutely delighted to have streaming internals, or at least SQL doesn't have anything to say against why you can't have streaming internals, and I'm going to call it a few cases where it's really handy for the internals to be streaming. So here's, again, Materialized, where we are, rather than issuing queries, rather than just saying select and pressing enter, we are going to create a view. So this view is a way in SQL to essentially give a name to a query and implicitly express to the system, yeah, this is interesting to me. I want to probably see the answer to this more than once. Yeah, maybe not. Certainly the materialized keyword, this is something that several databases support. And this tells the database system, not only am I interested in this view, I want you to go and figure out the answer to this and write it down, because I want it to be fast in the future when I ask for it. So it's essentially permission to go and execute this query. And in Materialize, we go further and say it's not only that, it's permission to, in an ongoing fashion, keep that answer up to date. So when you, down below, type select star from max temp by region, this is always fast. In Materialize, and in principle, potentially other similar systems, this will always be fast in that in one of these OLVM, these view maintenance systems, right? They will maintain max temp by region for you rather than go and reevaluate the query from scratch just because you've asked for it. So this will always be fast to read out these answers. And if you're lucky, it works nicely in Materialized is the only reason I have it here. These can also be nicely indexed and maintained like that. Pulling out a particular region, for example, from this result, because it ended with that group by, this is sub-millisecond times to get sort of the current up-to-date answer. Because it's just sitting there, and not as it's sitting there in a nice index that we can just dive into and just read out the answer. So this is sort of streaming internals inside a database. Like, rather than wait for a person to ask a question and then start to do all the work, we set up the ask ahead of time. We set up this view definition. System gets to work, and although I guess I haven't said it here, it only needs to do work when things change. And that's exciting. That means that there's now an opportunity for streaming infrastructure inside the database. All right. SQL systems are plenty happy to consume streams as input. You don't often think of, or I didn't often think of SQL systems in this way. I thought of, you just have tables, you insert into tables, that's it. But let's talk through this. So that readings collection that we had some sensors, and we got all these readings from the sensors, and that collection is going to grow. And it's going to grow without bound, probably. No one's ever going to delete readings. Well, that's exhausting, right? Like, do we really want to have to put a copy of that into our database? I mean, you might want to. That might be a good thing to do with the database, but we don't have to, right? In particular, if we know what we're going to do with these readings, we know we're going to just keep the maximum temperature. That seems like a terrible waste. So what you can do in Materialize, and there's some analogs to, let's see, in SQL to foreign data wrappers or foreign tables, but you can create in Materialize what's called a source. And a source is a named thing, it's like a table, but instead of being the data for the table, it's a description of where to go to get the data from. So this might be a Kafka topic, for example, or a logical replication stream coming out of Postgres, something like that. But it's a description of when you need to go look at the data, here's where you go to find it. Just because we don't happen to have it here, and we don't impose the requirement that we make a copy of it locally. So, maybe you won't actually choose to go and select star outer readings. And if you choose not to do that, if you go and just create the Materialized view down below, the max temp by region, Materialized is delighted to say, this is amazing. You don't actually need all of readings when we do this. We can just keep the maximum temperature for each region. Wonderful. Like this is great news. And that this is a really nice connection between streamed or sort of externally managed and then presented sources of data that make a query processor much more efficient in this case. We use a lot less memory than if we had to make a second copy of readings. And finally, at least for this point, SQL is totally comfortable with the idea that you might produce streams as outputs. And there's not really a lot to say here, unfortunately. It's a fairly terse command here, but there's absolutely no reason not to take one of these collections that are continually changing, a view, for example, the max temp by region view, and write all of those results, write that change log out to something like Kafka, or present it, potentially, we don't do this at the moment, but present it as a Postgres logical replication stream that you could then spin up a Postgres replica on and just serve the data out of that if you wanted. Yeah, it's a totally friendly concept. SQL doesn't say, no, you can't, you're not permitted to do this sort of thing. No, it fits really nicely into the setup, and it actually gives us a nice sort of end-to-end story about how you can use SQL to build this sort of streaming infrastructure. Let me little picture for that just to recap. You are more than welcome, just using SQL, to pull in foreign data from other databases, from Kafka, sort of land it in Materialize, maybe not make a copy of it, maybe feed it into some query, some business logic that you've described using SQL relatively tersely, which is delightful. And then rather than, you can hold on to that for sure and serve answers out there, but you can also dump that back into Kafka and let it flow downstream. And what you've done, which I think is pretty cool, is put together a piece of data infrastructure just using SQL and Materialize. And you can go get a coffee now and just sort of hang out. You don't have to write a script that continually fires this query off once every 5 minutes or any nonsense like that. In principle, the system is taking care of this for you. So I think that's a pretty cool way to approach. I'm gonna say like 95% of data infrastructure problems that are get a copy of some data, look up a thing in some other collection, and then hand the decorated result back out. All right, believe it or don't, but this is the SQL benefits. SQL benefits from streaming stuff. I'm going to spin it around a little bit and try to do it the other way. I do see that there's some questions. I wonder if I should. Let's hold off on them for the moment, because me actually clicking on the Q&A thing to see what the heck's going on is I have no idea how to do this in Zoom. But I'm going to leave some time for questions at the end for sure.
Well, I'll kind of keep track of them for you. Sorry to jump in.
Perfect.
I'll keep track of them so that you don't have to go through that. You can just answer them when
Thank
the
you
time
so
comes.
much. Folks should definitely ask questions, and I apologize I'm not going to be able to interrupt right at the moment and answer them. But I'm delighted to field any of these things when we get a free moment. Thank you, folks. All right, the flip side of this, I'm going to say, is that streams and stream processing benefits from SQL. Now, this is, the previous argument was maybe to the people who liked SQL and didn't see what streams could do for them. This is sort of the other direction. This is for people who are familiar with stream processing toolkits, things like, let's say, Flink or K-streams or other sorts of things, who might say, why, I use those things because I need power and ability. And I'm going to claim that you can do a lot of the cool things that you would do with a stream processor just using SQL. Just a little creatively use of SQL, but I'll show you some examples, and then again, you decide whether you like the answer or you don't. So why do people reach for stream processing systems? A classic answer, and one that actually we've already seen the example, is what if you have unbounded data? What if the data that are flowing in just append-only data, these readings, grows without bound? You really just can't afford to put this into an actual database. or maybe you could afford, but it's just obviously such a waste that you feel bad doing it. And this is fine. Like, SQL doesn't tell you that you have to use tables that make second copies of all of your data. You can absolutely create a foreign data wrapper to your stream. You can present this materialized view. And by being clear about what you're going to do with the data, we can bypass some of the potential issues you would have had if you tried to use a vanilla database, right? You would, potentially keep a second copy of the data. Materialize for sure is bright enough to go and do the pre-aggregation before the data even land in memory, to be honest, which is really nice. So we don't end up storing anything more than the aggregates we need to keep track of to maintain this view correctly as the incoming data change. So that's really handy. If you're worried about unbounded input data, that doesn't have to be a problem. SQL doesn't say that you're in trouble. You just need something that implements SQL a little different, a little bit more stream friendly. Let's do another example. So another reason people look at streaming systems rather than databases is that they want to focus on recent events, right? They want to look at customer events in the past hour rather than customer events in the past year. These sorts of things. A lot of this data is sort of more timely and relevant as soon as possible. And it's just fairly important to have tools that let you subset the data down to things that you're looking at in the very recent history. Let's take an example where we want to look at this max temp by region, but I'm going to add a new constraint to it. We only want to look at this aggregation over things that have happened in the past minute, right? Now, ignore the materialized view part for the moment. If we want to type in the SQL query to do that, we would just, we'd add another clause to this where clause. You can sort of see it commented out here. There's this MZ logical timestamp thing that just sort of blur your eyes for the moment and pretend that that's now. So that's the current system time. What the constraint is saying is, yeah, only include those records where when I look at the time associated with them, the time starts before now and 1 minute later is after now. So it's sort of there's a 1 minute window that each record contributes to the result. If you type that select query into something like Postgres with a now there and press enter, you'll see the right results. And if you keep pressing up enter, you'll see the correct results. What's sort of interesting is that even if the data don't change, the answer does change because the time moves forward. And that's a little crazy. However, it doesn't have to be a problem. So Materialize is bright enough to look at this sort of query and say, I see exactly what's going on with the time there. I'm not actually going to re-execute your query every millisecond. That's crazy. What I am going to do is realize that time ms and time ms plus 1 minute are very clear moments where I need to introduce your data at the first one and retract it at the second one. And I'll set that up for you. All right, so what you actually do get is this really nice 1 minute wide millisecond by millisecond sliding window over all these results that only does any work when new events arrive or 1 minute after a new event has arrived when we chuck it and remove some of the data. So it's pretty cool. You didn't actually need to use any new windowing, stream windowing syntax specifying hopping or sliding. It's just a slightly different constraint that you throw into the where clause and the system can figure it out for you. All right, now this next one, this is the hard one, but I think it's really cool. One of the reasons that people like to use stream processing systems is because they want to build an event-driven architecture for some of their data infrastructure, right? If you've got a SQL database, you can sit there and you can type queries and press enter to your heart's content. It's a little trickier to have live data prompt all of these queries, or at least things get a little scarier at that point. So sometimes folks go to streaming infrastructures because they want the arrival of data streams to provoke downstream computation and produce a stream of answers coming out the other end that they can then either land somewhere or serve back out to people. How do you do that in SQL? Turns out, works great in SQL using a cool tool that only makes any sense in one of these OLVM systems in Materialize. And I'll try to explain as we get there, but it's a query that you wouldn't, I think, ever bother to write if you're using a traditional OLAP or OLTP system. So let me talk you through this setup. We're going to try to put together some queries that are going to run our max temp by region, but only for a subset of models, right? If someone shows up and says, I'm query number 7, and I'm interested only in the models sensor A, and someone else shows up with query ID 13 and says, I'm interested in model sensortron or something, I have no idea. But we want to be able to support these sort of queries. We're going to create a new table, and it's going to contain queries by query ID and model text. Right, why do we do that? Well, we do that because there's a really cool SQL thing called a lateral join. And you may or may not know what a lateral join is. I certainly did not when, let's say 3 years ago. Morally, a lateral join is a for loop. It says for each record in queries, produce that record joined with everything that comes back out of the subquery over here, where, and this I think is the interesting part, where the subquery is allowed to reference columns in queries. So you can sort of see this second call out down here. We're actually using queries.model as an additional restriction in our query, and that's going to make sure that we only compute these results. In this case, over those sensors that have exactly the correct model. Now, you could probably imagine how you do this with an actual for loop, right? Like you would, sorry, I set a timer, it just went off in my ear. Where you could do this with an actual for loop, where you actually call SQL queries. That's expensive, that's annoying, you don't want to do that. So SQL allows you to instead say lateral join here. This is one query that essentially simultaneously comes up with all the answers to all the queries that you've got there. All right. Why would you ever use this? You would not probably use, like if you had a traditional database, or maybe like, an expensive, like slow but efficient OLAP style thing, you might bundle up a whole lot of queries and ship them off. So there's like 1,000 queries, send them all at the same time, get your answers back. You could totally do that. It's maybe not even a bad idea. I shouldn't have said that. What's really cool though, is when you think about what happens in one of these view maintenance systems. So let's talk about what happens. So queries is initially empty, right? So the output to this query is empty. There's nothing in queries, there's nothing in the output. As soon as you add something to queries, so if you add a new record, query number 7 with the model sensor A or something like that, the correct answer to the query changes, and it changes specifically by introducing in its output the correct answers for sensor A as the query model. So by dropping some data into, some data into queries, the result of the materialized view changes by exactly the answers to those queries. And this is true if you add a few more queries in there for different models, they will give you different, the corresponding different answers in the output. All right, what happens now? You just sort of hang out with your queries in queries. As sensors and readings change, the correct answers change also, and you will get a live stream essentially of all of the changes to your queries. So it's not really a query actually so much in this case as it is a subscription. Right? You're essentially subscribing to the answers to the subquery with a particular model associated with the sensor, and you'll get all those changes for as long as your query exists. If you want to unsubscribe to the query, you just delete your entry from the queries table. So I think this is really cool. This is a thing, in some sense, this is like a data-driven prepared statement, right? Like the query down there is very much like a prepared statement with the queries model being the held out variable. But instead of actually issuing them as prepared statements, we've set up a reactive data flow that gives you the right answers exactly whenever new queries show up, reusing existing data assets, and keeps you up to date as the other data changes. I think that's really cool. So that was the last of my points there, and I'm going to try to wind down to end cleanly in time. You can see that we weren't going to survive to the second section, but I'm happy to field some questions about it offline. The claim here is that you can write SQL, and depending on the data infrastructure tool that you have, like something like Materialize, you can actually make a really cool streaming infrastructure out of it. It can do things other than just answer SQL questions. It can focus your attention on recent results. It can distill down the data before it even lands in your system, and it can even let you write these data-driven or event-driven architectures for answering questions, which I don't know, all super cool. I am going to totally skip part 2. I apologize. I do want to end by throwing up. There's some really good stuff in here, though. It's really nice. Throwing up the final slide, which just calls out how to get in touch with us if you're interested. Ta-da! Right. I'm going to stop here. Materialize, we're definitely hiring worldwide. If folks are interested, reach out and get in touch. If any of this actually was interesting from a technical point of view, feel more than welcome to reach out and get in touch. I've been repeatedly surprised and delighted by how well this different take on data infrastructure, so reactive databases, have fit into the existing stacks and what people are currently feeling the pain about with respect to getting their data to do what they need. I'm McSherry at Materialized.com. It's a great way to get in touch with me. And shamelessly also jobs at Materialized if you're interested in that. But
Excellent.
That's what I have for you. And I'm gonna stop.
Great. Thanks for an awesome presentation. Just want to make sure everybody can hear me. And by the way, if you do presentation, you are allowed to shamelessly market yourself, your project, your company. So this was very much in the sort of is very much in line with what we expect. We have some good questions here. I'd like to take a couple minutes and make sure you have a chance to hit them. Here's one. How do you deal with exactly once and duplicates in that stream processing?
Great. So this is a question. Hopefully I'm not going to misinterpret this, but a classic problem in stream processing is that the underlying media, it's like Kafka, for example, doesn't usually guarantee that it'll only show you of a particular record once. And it might show you multiple times because of failure things. It's just hard to be quite sure, especially in a distributed setting. The good answer here, the fortunate thing is that folks have built up an understanding of how to deal with this. You have to do a little bit of integration with your applications to, like all these messages, for example, are going to have morally the equivalent of sequence numbers. In Kafka, there'll be offsets. And you need to make sure to essentially deduplicate the offsets as you see. Kafka might roll back its cursor. You need to say, no, please go back to where you were. Don't screw up. Many of the change data capture protocols will have this built into them. So Debezium, when it captures data, will have very specific identifiers associated with each of the transactions that it's captured from upstream. And hopefully no one has given you two different transactions with the same identifier so that it's safe to deduplicate by transaction identifiers. If no one's done this, yeah, things are a bit of a mess. So if the data in Kafka are just piles of text and, hey, maybe someone said cat, dog, and you're like, is that one cat or two cats? I don't know what you meant, right? So you do need a little bit of help usually in terms of, a nice clean upstream source of data being crystal clear about what gets presented. And if you have that, it's usually not so bad. You do have to pay attention. But if you don't have that, things are less predictable, let's say.
Okay, great answer. Here's one coming in off YouTube. What happens if we add queries after some of the data relevant to those queries has passed by?
A great question. Different people have different takes on this. Materialize will give you the correct answer. So the data that flows into Materialize, if you have said, I want this, like I want to, this is a source, I'm going to allow people to use it, we will capture it and we will keep it there for you when you choose to go in and use it. We don't, or we strive very much to not give you wrong answers. And that's part of the sort of usability contract. If we gave you bogus answers, we would very quickly not be a very popular database replacement. I mean, you'd be a fine stream processing tool. At that point, you'd have a user menu with a whole bunch of asterisks in it at the bottom, and we're trying very hard not to do that. So if you pointed us at the Postgres logical replication log, data might flow past. If you come and try to use it again and we've lost track of that data, we will reconnect and re-snapshot and pull the data back down again. Yeah.
We'll take a couple more quick questions and then we'll switch over to Pavel. Pavel, if you want to go ahead and bring up your slides, then we can keep moving. Let's see, the YouTubers are getting feisty. We've got a question here.
Sure.
Do you support window functions?
Some of them, yes. Now, the interesting thing is like, we support a bunch of them, though that's different from saying we support them really well and you're going to be delighted, right? So there are window functions out there like median or something like that, or associating the rank with every object. It's ordinal to like 1, 2, 3, 4, whatever. This is a thing that can change dramatically if you add one more record. And so we will give you the correct answer. That doesn't mean it will be fast. Like you may have asked a question that's just really hard to maintain incrementally. We choose to give you correct answers rather than quickly give you the wrong answer. Personal choice. And yeah, in many cases, I think your window functions will be fine on relatively small windows and start to catch on fire if you apply a window function to your entire file of data. That being said, if you're trying to use window functions by time, I strongly recommend you look at temporal filters rather than SQL window functions.
Good. Final question. What protocol is used to communicate from sensors to Materialize?
Sensors. So I would say sensors in the example, maybe it's a bad example.
I think it's in
sensors
it's coming from your example.
sensors are not directly communicating with Materialized. So in this setup, sensors would be dropping their information into something like Kafka. So that would be the sort of the rendezvous point where some other harvesting process upstream is pulling in these measurements, landing the data in Kafka, and then Materialized is able to pick it up from there. I definitely wouldn't recommend trying to get your sensors to directly communicate with Materialized. It sounds like that's likely to result in some data loss somewhere. It's really helpful just architecturally to have sort of, I think of sensors as unreliable, have them land their data somewhere that as quickly as possible we can agree, good, stable, durable, as opposed to having 100,000 things try to connect to Materialize and time out and who knows what. Yeah.
Okay. With that, I think we'll call it good. There are a couple more questions out in the Q&A box. If you want to go ahead and just type the answers in at your leisure. What I'm going to do now is go ahead and do a switcheroo on the OBS recordings. Give me 1 second here. So thank you very much, Frank. Great talk. Let's go ahead and.
Thank you for having me. I appreciate it.
You're most welcome. Okay, for our next talk, it is my pleasure to introduce Pavel Odintsov, who is the author of FastNetMon. He's going to talk about what FastNetMon does, DDoS protection, and how they use ClickHouse. So Pavel, go ahead and take it away.
Hello, everyone. I'm Pavel. So I work for FastNetMon, and I wrote original version of FastNetMon. It was started about 8 years ago. Quite long time. And when we actually started, our main mission and goal was to help our customers to detect DDoS attacks. But it changed in this time, and I'll introduce you like how our project involved, what kind of challenges we had with data processing, and how actually we find our company as data processing company more than cybersecurity company. So our product uses open core approach, and we have great communities. We have great bunch of people who actually really passionate about DDoS attacks, processing data. And all the time, I will be more than happy to answer any of your questions. So you can find all my social media contacts. So all the time, if you want to talk with him, just drop me a message. And what is FastNetMon? Actually, it's a tricky question because for 8 years, it changed a lot. Originally, FastNetMon was started as DDoS detection tool. It doesn't sound relevant to this meetup because we're talking about data. But this time, because of demand of DDoS attacks, and a DDoS attack is quite abstract thing because, all the time, if you experience DDoS attack and if you're familiar what kind of DDoS attacks your network experience or your company experience it's just beginning. It's just beginning because all the time, after a company was hit by attack, we need to write postmortem and we need to provide some insights. What actually happened? We need to provide great visibility about the dynamic of attack. And that's how we started adding more and more features like traffic visibility. And for now, as part of our project, we offer different types of cloud visibility. We can ingest logs from Amazon AWS, VPC flow logs. We support the same VPC flow logs from Google Cloud. And in addition, it's more for on-premise deployments and for telecom operators, we have great support for BGP protocol. And so from this perspective, FastNetMon can be explained as tool, as network automation tool, which can run some specific actions in response to some dynamic changes in your network. It sounds quite complicated. And for my next slides, I will try to explain what we're actually doing. So let's share how FastNetMon works. I expected this diagram may scare people. Let me talk a little bit around it. What is it? Because we are talking about data, and in the center of this diagram, you can see FastNetMon. Just to explain what FastNetMon is doing. FastNetMon is a great aggregation engine. So what we are aggregating, why we are aggregating. So on the left side, we have different data sources. And when I say data sources, and of course, what kind of data they produce. And on the top of my slide, you can see example of data, what we have in place. So from left side, you can see switches, network equipment, boring, routers, boring, some data sources from public cloud providers. And from their side, we receive information about traffic. So in quite terse format, network equipment or cloud itself, they provide information, what kind of packets, what kind of network packets they receive it or send. And then this information may be used in different ways. Just to explain in well-known words, what kind of data we have inside. Inside of information received from equipment, we have source IP, we have destination IP, we have source port, destination port, number of packets, packet length. It's not very specific for networks, and everyone working with cloud environments, they are very familiar with what kind of packets we have. They may be UDP packets, TCP packets, all kinds of them. And what is tricky about it? Why we cannot like read this data directly? Why we have so many formats? Because network equipment is implemented very efficient way, which is efficient not for human beings, but efficient for hardware to generate. I would call it's not just developer unfriendly, as typically we explain data in quite not nice format. I would call it developer hostile formats, because many vendors, they interpret interfaces different way. They encode data very different way. And that's actually reason, and again, with public cloud providers, all of them, there are no standard about ways how you can actually export data from cloud provider, because for routers and switches, we have two different families of well-known protocols like SFlow and NetFlow, but for cloud providers, there are no protocols. It's something in JSON encoded in quite a vendor-specific way, which is under control of specific cloud company, and so it makes things complicated, and especially because many large companies, of course, you may know that like lots of companies, they run completely in cloud, but more than about large companies, very large companies, they have two approaches. They keep on-premises in infrastructure, and they keep cloud, and that's how problem begins. So we need to ingest data from different network equipment. We need to ingest data from network routers, from different clouds, and then we need to aggregate it. What I'm saying, what do I mean by aggregating this information? Because from the left side, if we ingest information about packets, like packets arrived right now, then more like 5 more packets arrived, 10 more packets. But this data is not useful for us, because for many real applications, it's not important for us how much traffic specific IP has. Like we don't care. But more useful and more real application, as they need data in different format. Actually, what we need to calculate what is the velocity of specific data stream, because like that we had some like random number of bytes for specific virtual machine in Amazon. It doesn't say anything, but that's why we actually inside of FastNetMon we have very high efficient flow parsing and flow aggregation engine, because as first level, because we have different protocols, we aggregate, like we process data in same format, which is unique for us, but it's standard for every single protocols we have. And then we aggregate this data. And when I say aggregate, so instead of input information, what you can see on top of this page, it's like how much bytes we have from specific IP, what kind of protocol. But after FastNetMon's processing, we have it different way. So instead of saying like we received 5 packets for last 5 seconds, it doesn't say anything. We can say it in very, very more useful way. We can say it like for specific host, which is an example 10, 1, 2, 3, we received 100 megabits of incoming traffic and 200 megabits of outgoing traffic. And what actually happened inside of FastNetMon, we aggregated data for specific host for a specific period, and then we calculated it. So, and then this data may be used for different approaches. It may be used for DDoS detection, because we may check, is it like malicious flow or not? Or we may think, we may change something about this traffic, or we may decide to block it completely. And this one is just one of the levels of aggregation, because network, like everywhere in networking we operate not only on basis of IP addresses, but more of basis of prefixes. And FastNetMon can create any number of different aggregation on network basis. So instead of like just calculating what was incoming bandwidth, outgoing bandwidth for just single host, we can aggregate, for example, for a set of hosts or specific /24 network, which has 255 hosts. And then according to this information, we may decide about it. Again, you may create some specific group to understand like what is the traffic for your specific front end, like, because you have some expectation that it may generate like 100 gigabits, and then you can see significantly more or significantly less. You may, for example, even create Prometheus alert, or you can just notify your network team like something going on. And that's why this talk, you hear this conversation deeply about networks on this meetup. We need to store this data. That's how our journey started. So our journey started from Graphite, and then we moved away from Graphite to InfluxDB, and where are we now? Right now we are on ClickHouse. So why? How it was in dynamic? Let's move forward. My explanation was, I suppose, what cost abstract. That's what system administrator see when you're on a FastNetMon. Like this one is just number of incoming packets per second, outgoing packets per second, megabits flows for every for all top talkers in your network. And just to understand scale, even in quite medium-sized network, you may have millions of active hosts. So now you can understand what is the challenge. And what you can see on this screen, it's top K request over millions of hosts, which may be tricky. So, and I will explain why it will be tricky. So you can understand like what kind of data we have, but on this screen, it's just a small chunk of data we have in FastNetMon. It's just one of the levels of aggregation, and we have way more of them. So, because FastNetMon, it was built for DDoS detection, and DDoS detection in case of FastNetMon is quite simple. It's not about machine learning, like artificial intelligence or some heuristics. It's just about specific actions. We call them thresholds. You set threshold and a specific level of abstraction, aggregation, for example, IP address or specific network or group of hosts exceeds specific value, like your backup server exceeded more than 1G of capacity, and you never expected it to do it this way. And then you need to alert your network administrators and then do what we can do and why it happened. That's how it works. Very simple. And because of customer interest in all our aggregation, instead of just offering this information somewhere inside of FastNetMon, we realized that we need to expose as much as possible data to customer. And you can see here, it's like, it's not very well known product called Grafana. So, and you can see different level of aggregation. So left side, it's highest possible level of aggregation, just total traffic, how much we have incoming, outgoing. On the right side, it's aggregated over different prefixes. And again, even like medium-sized network may have hundreds and thousands of prefixes or even more. And on the right side, right bottom side, it's a worst possible scenario. It's specific host. And again, we may have tens of millions of hosts in our network. And we need to store all this information somewhere. And it was a challenge for us. So, and this one, because previously on previous slide, it was just like specific traffic for specific prefix, specific IP address. But this one is more complicated. This one is what we call top K request. And that's how we actually kill our databases we used previously. It's very easy because we need to select from enormous data set. We need to, in this example, we just to select just 10 top hosts or top entities by traffic. And it puts lots of challenges for us because for customers, it's most interesting request because all the time, if something weird happening in your network, you need to find out like what is the largest source of traffic or target of traffic, and then you run top K request and try to find out what's going on. What is the problem? When I mentioned that like lots of different devices or public cloud send information to us, I didn't mention scale. We are talking about one of the largest deployments of FastNetMon. It has 1.5 millions of incoming messages per second. And they have more than 16 millions of unique active hosts in their network. And it puts lots of challenges, how we actually just receive this data, how we parse this data, and how we actually aggregate this data. And back in time, so it was one of the problems. And second problem is that we store traffic because we have no option how we can actually compress this information. It's not some specific value which can be put in some like small value like unsigned int 8-bit or something small. And we need whole range of unsigned int 64-bit values. So not so many options how we can actually compress the data, and data arrives in large data sets to us and customer like top key requests. And we need to do something because we cannot just drop like, don't run top key requests because it will kill our engine, it'll kill our product, and you will not able to receive this data. We need to do something. We need to offer customers something. And we did. We started with Graphite. It was more than 7 years ago, a long time ago. And back in time, I suppose we haven't got great choice of options because when you Google TSDB in back in 2015, and then I suppose only Graphite came up. It worked well for us for a very long time. And now, of course, on this slide, I mentioned a few most annoying features for us. And first one, of course, it's dot as delimiter of metrics, because we operate with IP addresses, which use dot as delimiter. And same with prefixes. I also use dot as delimiter. And all the time it was quite annoying. Instead of using something like 10.00.001, we have to use 10_0_0_01. It's annoying, but we can live with it. But our largest problem with Graphite was performance. Quite fast enough, we realized that we cannot scale it more than 200,000 metrics per second. And we tried to find out options, what we can do. And we found some of them. And so that's how it was in 2015. Just to imagine, like I previously showed you nice dashboards from Grafana, but it was a real user interface of our product because for Graphite we had only option, and Grafana was started, I think, one in 2016 or around that time. It wasn't very known project back in time, but I'm very happy to see like existence of Grafana because it's great, because you don't need to deal with something like this one. It worked, but you know, you need to create dashboard all the time manually for every year case. And so we hit performance limitation. So you can see how much CPU carbon cache uses for this specific case. It wasn't large deployment of FastNetMon. Literally, it was one of the test labs we used for testing our product. It had just a small network as input of traffic. But you can see it's 21% of CPU. It's not that much for FastNetMon, but problem is carbon cache is single-threaded, implemented in Python. And so just like multiply it by 5, and then we will reach limitation of single CPU core, and then after that we're out. So we have no options how we can actually scale it more. And of course we must scale it more than 1 million of metrics. We have way more of them. So like our first optimization was quite fast. We realized like Python, what you can do with it? And here you go. We found a great project called GoCarbon. It's literally, it's re-implementation of metrics daemon used by Graphite in Go language. And you can see for exactly the same load of 200,000 metrics per second, it's just 10%. So this way we were able to scale up to something like 2 million metrics per second. It wasn't bad, it wasn't good, it was something to work with. It was great for beginning of our product, but we got more and more larger, I mean, medium-sized and larger customers. It wasn't enough for them, and we tried looking for different options. In FluxDB, so it worked very well for us. It was really great for deployment perspective because it's just single Go binary. It works on every platform. No need to compile, no need to install some custom repos. Just drop binary and it will work fine. But problem is, you can see lots of our complaints about InfluxDB. But for most of the cases, InfluxDB worked way better for us in Graphite because it used a way more compact approach for storing data. It was able to process more data. But unfortunately, we hit limitation of InfluxDB quite fast because around same numbers as Graphite, it wasn't able to process all data. And we started looking for different options. And unfortunately, for quite many years, we had no different options. We just like tried to live with InfluxDB, and we had plenty of problems with InfluxDB. One of the most annoying is that you just stop InfluxDB daemon and then you start it again, and you need to wait something like around 15 minutes with not such large data set. Like, I mean, not our largest customers. And so we tried to find out what is the options we have. And surprisingly, we realized that ClickHouse is just great for metrics, just wonderful. Again, like greatest feature from ClickHouse, we can stop thinking about cardinality. Like really, let's compare. Its diagram just compares like what was our experience with InfluxDB and what was our experience with ClickHouse. And cardinality is one of the largest problems for us because even medium-sized network may have tens of millions of hosts. And I'm talking about protocol of IPv4 because for IPv6, it may be hundreds of millions of unique metrics and like unique hosts in network because they may be allocated per service base, they may be randomized, different options. And from our experience, InfluxDB explodes and dies around 1 million of unique series. That's all, end of story. But we need more, we need way more. And we just want to stop thinking about what our cardinality is, because it's completely unpredictable for us, because it may be small network, it may be an enormous like network. And then all the time we need to change how much text, how much like unique series. Well, it's hassle. And in ClickHouse, we don't care. And it works with any level of cardinality because it's not exactly a time series database in terms of what like we had under impression we get managed to something. And so, and bandwidth of ClickHouse is just enormous. We had no customers who actually reached scalability limitation for ClickHouse. I'm pretty sure ClickHouse has some of them, but I suppose it should be an enormous number because for now we have plenty of active deployments handling more than 10 millions of unique series per second. And ClickHouse is not like largest contributor to CPU and disk load on those machines. So it just works fine. And so we have no problems with stop key request. Of course, it's need time because it's need to read lots of data from disk space, but it can be finished in reasonable time. And when I say reasonable, we are happy even if it finishes in 5 minutes. With InfluxDB, it finishes typically in with or out of memory crash or just daemon hang up. That's all. No options to just, but in ClickHouse we just wait. It's a little bit longer, but it works perfectly fine. And so our choice for metrics now is ClickHouse. But was it that simple for us to introduce ClickHouse as metrics engine? Like roadblocks, scary name, but actually most of my tickets to ClickHouse just complete most of the nonsense. Like, because you can see here just two different questions about how I can actually compile. It's on ARM64 machine because, you know, we offer our product on ARM platform and we need to like offer like our database on ARM platform. And so I started like chasing folks like, can I compile? How I can compile? And so I got my response. And second case, it was mostly just miscalculation, like misconfiguration on our side. We actually tried to push more data sets, like more columns than we actually have in database. And that's why we kill it. And two of them, just a few minor things. So it was completely like, it was very simple for us. No roadblocks, no blockers, no complicated things. But what was unusual? Unusual was that we can actually get rid of cardinality problems. And it opened a great way of using ClickHouse, not just for metrics. Also, we can use ClickHouse to store every single flow we receive from network equipment or flow from cloud VPC endpoints. And on this slide, you can see exactly the same data as I explained on the first slide. It's source IP, destination IP, some meta information like input protocols, TTL, and we can put this data into ClickHouse easily. So it's not limited just to keep data which was pre-calculated by FastNetMon. We can actually keep push raw data in the database. And it wasn't simple. This one, in this case, we have to implement different approach to aggregate data again. So that's why I call FastNetMon as great aggregation engine. So we need to aggregate on different levels, because when we push metrics about what is the bandwidth, what is the packet rate for specific IP address and network, we do calculation just once per second, and then we push every single metric as enormous blob of data to ClickHouse. Previously for Graphite, or in fact, it was a problem because even their protocols, they expected to have some reasonable size of inputs data sets. But what we push into ClickHouse, sometimes we push multiple gigabytes of data, and ClickHouse handles them very well. But problem with data, because we receive flows one by one, and we cannot insert them into ClickHouse one by one, because that's not how ClickHouse was built for. And this one was quite tricky for, I would say it wasn't quite tricky for us, but we had multiple mistakes. So first thing, we tried obvious option as buffer table. Unfortunately, it didn't work for us well, because maybe, I don't remember reasons, but it's failed to insert everything what we need into main table. And then that's why we implemented our custom implementation, because we share same language as ClickHouse. We use C++ for development of everything in FastNetMon. And we just created buffer, which typically creates batches about 10,000 of different packets, and then pushes them into ClickHouse in single transaction. And from our side, it was just single, I would say, thing which was different from databases we used before, because we expected that we need to push every single packet one by one. And quite fast, we realized that it's not working that way. It's not that efficient. And when we switched to new approach and create enormous batches of packets, it started working just wonderful. And so it's not just about storing data, because with many databases, you actually can put lots of information into database, but when you start reading it, you can expect that dataset to explode, or it will not finish ever, or it will just, lock, because the amount of data is enormous. But with ClickHouse, it just works just wonderful. We have many customers with data sets exceeding tens of terabytes. And because of data is shared over day basis, monthly basis, hour basis, it's extremely fast for FastNetMon. Even make some crazy requests, like select every single flow for last day and count how much traffic we had from Google. You cannot imagine this kind of request previously, because it will kill your database immediately. It will explode because of enormous a number of disk reads, or you run out of memory. But this ClickHouse, you just need to wait a little bit longer, maybe half minute, and then here you go. And even with distributed setups with many machines, it can be so fast, really. So, and even better, it's not enough for command line, and because this one is crazy SQL syntax, which is for many people is still quite complicated. And we can do it from Grafana, which is great. So same data, it can be filtered on different boundaries, different levels. You can receive this data with great precision. You can say for sure how much your customers or your virtual machines did request to Google's 888 service, in specific amount of time. And you will get this information. It's just great for security purposes, for audit purposes, or just for out of curiosity, because it's nice data to have. And we are really happy about ClickHouse, and our experience with ClickHouse is just great. And so we have really large community built around of FastNetMon. Most of our folks are network engineers, data center operators, different ISPs, cloud companies, and many of them are making great steps into data because everything is data. So they're trying to move from old pipelines of data processing built by their vendor, and typically they look like black boxes, like you cannot change anything. Instead, many of them just moving to something well-known in industry like Grafana, Prometheus, InfluxDB, ClickHouse, and they're trying to work like leading industry standard tools to work with data. And typically back in time, nobody used data processing tools for work with network data. It was just completely isolated set of tools. But what we can change now, it changes, and we can use exactly the same tool for working with network data, on different kinds of financial analytics, advertisement, just many types of data, and we can unify it this way. And thank you for listening. And if you have any interest in network security or DDoS attacks, join our communities. We have a great set of people, and we will be happy to share our ideas and our experience with FastNetMon. Thank you.
Thank you so much, Pavel. Great talk. We have a couple questions. So one here is, why did you not convert the IPs to ints? That's first one that came up early in the talk.
In which I support, let me show. Actually, I think we do. Actually, yes, we do convert them into ints. So
okay.
for storing a database, we convert them into ints. But in one case, actually, when we save them for metrics names, because metric name can be literally anything. It may be just like short name, it's maybe just name, Latin name, short name, and that's why in this case we use just strings for customer convenience, because then in Grafana they will be able to find out like it's not just like 1, 2, 3, 4, 5 and something like meaningful for customer.
Yep. Good. We'll take one more quick question. Pavel, what is your order by in your main table? Which I take it we're looking at that right now. How did you get to this order by on the first, right from the start?
Not actually. It's actually one of the things we change quite frequently, because for different companies they have different interest in like this one. It's like because current one is about source IP and destination IP, because like most of our customers are interested in checking what was data exchange between specific IP addresses. But for many customers, they are looking for different options. That's actually why in our product we offer options to override it. And a customer can create and change order by for their own purposes, because, and also we have different case actually. We recommend customers to create different code duplicates of same data, order different ways. So because if customer want to keep option to select data by source IP and destination IP, but in same time they want to have very fast access using for like source ASN and destination ASN, they literally just duplicate data just to keep it fast, or they just change default order key.
Okay, great. We'll have to close there because our next talk is coming up. Thank you so much, Pavel. If people have other questions, feel free to put them in the Q&A box.
Thank you for inviting me.
You are most welcome. It's been a pleasure having you. I'm going to do a quick switcheroo on recordings. 1 second here. So we'll go ahead and terminate this one. And we're just closing that out, and I'll switch in OBS Studio so we'll get a clean recording for for Alexey's talk. It seems to be taking its time stopping. All right. Okay, it is my pleasure to introduce the final talk today by Alexey Milovidov. He will be talking about the ClickHouse 2022 roadmap, and I'm not going to say anything more because Alexey's going to explain everything. So Alexey, welcome. It's wonderful to have you.
Thank you. Let me share my screen. Okay, now you see it.
It looks great.
I will tell you about the most interesting features from the past year, 2021, and the most interesting features to come in this year. So let's start. By the way, it's very difficult to choose some favorite features of 2021 because we have too many of them. And I want to ask you a question. You see this list, and could you please select one? What is the most interesting feature for you? For example, Robert, what is your most interesting feature of year 2021?
I want to hear about UDFs.
Good choice. By the way, for me, the most important feature is window functions. But there is almost nothing to discuss because they work as expected. They correspond to the SQL standard, and that's it. Nothing to discuss. Another quite interesting feature, maybe you have missed it, but I hope you did not. It is also related to SQL standard and to the quite modern SQL standard is support for SQL JSON. We have JSON exists, JSON value, and JSON query functions. They are quite easy to use. One argument is your JSON, and another is something like JSON path. The function will extract whatever you want, transform, and return the result as expected. And this is probably quite small, but it is also very important. It's about the language for server configuration. ClickHouse usually has XML configuration files, and sometimes I meet people that tell me that XML is not longer fashionable. It's not trendy. It is so outdated. I don't get these arguments, but still I respect these people. So for these people, we allow to configure ClickHouse with YAML. The same configuration, but in different language. It is more compact. And if you use something like Kubernetes, you will find it convenient that you can have everything in YAML. What about security and compliance? For this, we have support for data encryption, full disk encryption. It is quite easy to configure and easy to use. You just configure a storage policy that contains encrypted disk, and every disk can be encrypted. So you configure encrypted disk on top of another disk. And when you store your tables on this disk, every file will be automatically encrypted. You can provide your encryption key basically from anywhere. You can put it directly in configuration file, but it is not secure. Instead, it's better to store encryption keys somewhere else and load on server startup from environment variable. We also have per column encryption. If you want to encrypt just a single column with some sensitive information and leave other columns unencrypted. What is also interesting that full disk encryption almost does not affect performance. So performance is almost the same. The difference is typically just a few percent. So it is very interesting. And about some interesting integration features, I want to again ask Robert. Robert, I know that your favorite analytical database is ClickHouse. Is it true?
It is completely true.
Yeah, and what is your favorite OLTP database?
I have to confess, it's MySQL.
Okay, it's my MySQL. So
yeah, I think one of your favorites too.
Yeah, it's also my favorite, but we have developed this integration, not for you.
That's right, for my friends. That's
okay, yeah. For your friends. Because native integration with MySQL already exists, already existed. But now we also have native integration with Postgres. You can use Postgres table engine and table function, and you can query Postgres directly from ClickHouse. You can read and write your data into Postgres. You can even join Postgres tables inside ClickHouse, because you know what? Maybe ClickHouse can do it better, but not necessarily. And if you want to join Postgres table, MySQL table, ClickHouse table in one query, you can do it in ClickHouse. You can even create a database with PostgreSQL database engine. It will automatically load every table in Postgres database and represent these tables as ClickHouse tables that will do queries on the fly. Also, we have Postgres as dictionary source. And finally, ClickHouse can mimic to be Postgres. It has support for Postgres protocol. You just specify PostgreSQL port in configuration file, and ClickHouse will pretend to be Postgres by protocol. By query language, you still have to write queries in ClickHouse dialect, because you know what? ClickHouse dialect is better. At least I think that. So plenty of options here. And we also have streaming replication from Postgres. It is like change data capture. So ClickHouse will subscribe to Postgres tables, load data, store into ClickHouse in more efficient format, and your queries will become faster. We have plenty of integrations, and Postgres is just one of them. We have relational integrations with relational databases, key value and document databases, streaming systems and queues, object storages. We integrate with any database with ODBC and JDBC interface. So ClickHouse is pretty rich. And finally, the favorite feature of Robert Hodges, user-defined functions. Now ClickHouse has support for functions that you want for your own scenarios. We have two variants. First, you can create a function using SQL expression like this. By the way, why this strange function exponent plus exponent of minus x divided by 2 is named ch. Do you know? If you know, please write into our chat. If you write the correct answer, maybe Robert will offer you some gift. Maybe not. I cannot speak for Robert.
So we'll gladly do that. So I see CH equals hyperbolic cosine.
This is absolutely correct answer.
Okay, Alontai, we're going to have to figure out some sort of suitable gift for you.
Yeah. CH is also ClickHouse, but it's not for this name. You can also create a convenient name for your dictionary. So you don't have to write this. You will write just this. If you create a function with a SQL expression, you cannot use something like for loop or some complex conditional state, complex control flow logic. And if you want to do this, you have to use scriptable user-defined functions. What it is, you can implement it in any programming language of your choice. In this example, we use Oak. Yeah, Oak is also programming language. But you may prefer something different like Python, Go, Rust, whatever you prefer. So we specify the name of our function, the type of argument, another argument, return type, the format in what data will be passed into and read back from this script. What will happen? ClickHouse will run this script, serialize input data, and read back the result that this script will have to return. What else? We also have user-defined table engines with scriptable tables. You can create a table with executable engine and provide your script and your data format. This script will generate data on the fly, return it in this format, and ClickHouse will read it. This is good for data generation, and this script can read this data from whatever data source. It can also be used for data transformation. You use the same executable table engine and also specify one or multiple subqueries. ClickHouse will process these subqueries, read the data, pass it into the script. The script will process this data and return to ClickHouse. So you can use it for any kinds of data transformation, maybe for applying some machine learning models. Quite interesting. You can even implement custom logic for joining multiple tables. And it has two options. One will run this script every time, and another will keep a pool of persistent processes. So pretty many interesting applications like querying, doing DNS requests or WHOIS, or machine learning, or integrating with foreign data sources that we don't support yet, but you can implement it. And this is also my favorite, one of the most anticipated feature. it allows you to do many small inserts into ClickHouse. You used to know that if you want to insert data into ClickHouse, you have to collect it into batches. And friends tell friends that always insert data into ClickHouse in batches. But this is not longer necessary. Now you can just enable the new asynchronous inserts feature. After you enable, ClickHouse will automatically combine multiple small inserts together and insert into table in some batch by itself. And it is also safe. Imagine 1,000 of clients send inserts into ClickHouse at the same time. ClickHouse will receive these 1,000 inserts combined together right into the table. The table will save it into file system. And only after that, each of these 1,000 clients will get confirmation of inserts. So it is safe.
A quick question, which is coming up.
Okay.
This is apparently, let me just read them out. Two people asked the same thing. Do async inserts only work for HTTP clients? And if so, why is that?
Since version 21.11, it works only for HTTP. Since version 22.2, that will be released tomorrow, it will also work with native protocol and ClickHouse client. What is the reason? It works when you have the data for insert in one packet. So if data is inside insert query in whatever format, maybe values format, maybe CSV, maybe native, it will be extracted and combined from multiple clients. But in native protocol, you usually send data in separate blocks. And this case, for this case, asynchronous inserts are not applicable. But since version 22.2, you can enable asynchronous inserts for ClickHouse client, and ClickHouse client will send the data with inside insert. Okay, maybe this explanation is not quite clear, but let's go on. What about interesting protocols inside ClickHouse? Now we have support for gRPC protocol. What it is? It is more sophisticated, more feature rich than HTTP protocol, but it is also more recognized, more standard than native protocol. And from performance standpoint, it is more close to native protocol than to HTTP. So if you use some programming language that has good gRPC library, this is like Go, Java, and Rust. I advise you to use gRPC protocol if there is no good driver with a native protocol. Okay, and some features of year 2021 was experimental, but they are going to graduate in year 2022. And there are 4 such features that will graduate very soon. First, ClickHouse Keeper, our own replacement for the Keeper. Second, projections, the way to have multiple physical representations of your data in a single table, like multiple orderings, or some aggregations for your data, like materialized views, but better. Third, replicated database engine. When, if you create a table, drop table, and do any DDL operation, it will be automatically replicated. So not only tables, but also databases will be replicated. And probably the most interesting and the most mysterious is virtual file system over S3 object storage. I will explain it in more details later. But now let's look at projections. Projections has been developed and contributed by my friend Amos Bird from Beijing. It was available since version 21.6 more than half a year ago, but it had experimental status. And now we have made, actually Amos Bird have made it to pass all the tests if it is enabled. And we are ready to make it enabled by default. So if you compare projections and materialized views, how is it different? First, projections are always consistent. With materialized views, you have to worry what will happen if data will be inserted into table but did not insert, have not inserted into materialized view. There will be a chance of inconsistency, but projections are guaranteed to be consistent. They are updated atomically with the table. Whenever you inserted something into the table, projections are also updated. They are also automatically replicated with the table because they are inside the table, not outside, like materialized views. And select queries can be automatically optimized to benefit from projections. And this is about object storage, decoupled storage for ClickHouse over S3. This feature has existed for almost 2 years already, but some of advancements has been made only recently, like performance improvement of select queries by implementation of concurrent asynchronous reads, like parallel processing on multiple replicas. This is available since 22.1, like caching for object storage in RAM or local disk. This is scheduled for 22.3 version in March. And some advancements about coordination for replicas. This is scheduled for the second quarter of this year. What is interesting that we have already achieved higher throughput than in typical EBS volumes. So if you have at least 10 gigabit network, if you have 10 gigabit network, it is the throughput will easily saturate this network, so it will be 1.2 gigabytes per second. Not bad at all, and it will be even better if you configure ClickHouse with 25 or 100 gigabit network. As a bonus, we also implemented a special type of virtual file system that is named web. What it is, you can export your merge tree table in set of files that can be hosted on a web server like Nginx. And then you can quickly attach these tables and you can read from them just like from local tables, but every time this server will be queried with range requests, and it can work quite efficiently. By the way, now it is faster than S3, but we are investigating why exactly. S3 should have the same speed. So we have our roadmap for year 2022. You can read it, but you may have noticed that this is already February. So 1.5 months from year 2022 is already complete. And we started delivering features from our roadmap. And the first features delivered is schema inference and parallel processing on replicas. Let's look in more detail. About schema inference. I am just excited about this feature, and you will know why. Until recently, if you want to use table function that is reading from file or URL or S3, you write the URL, the data format, and data structure. And data structure can be quite large because usually you have wide tables in ClickHouse. It was before like this. Now it is much more easy to use. You just write URL and nothing else. And everything else will be auto-detected. Compression will be auto-detected. Data format will be also auto-detected. And data structure will be detected from this format. This is so much better than it was before. It even works for JSON and CSV. It will do schema inference. You know that CSV is unstructured data format and JSON is semi-structured. But we don't afraid. We don't afraid semi-structured data formats. We will derive the schema and ClickHouse will be happy to process it. And as a bonus, if you create replicated table and when you create not the first, but the second and third and so on replicas, you don't have to write schema at all. It will be inferred. And the same for distributed table. You don't have to write schema. It will query the remote table and copy the schema from it. It's so much better. Okay, and we have plenty of features still to implement in 2022. And I have a huge list. I don't have a time to explain and to describe every feature, so I want some help from Robert.
Okay, I've got three. I want to vote for the three in the middle: transactions, semi-structured data, and backup and restore. Those all sound great.
You are
And
you are so greedy.
I am. And you know, I like semi-structured data because, by the way, oh, and we're getting Todd. We got Todd here weighing in. He wants backup and restore. By the way, the schema inference is brilliant. I think that's usability feature of the year. I'm going to have to rewrite about 3 years worth of slides because all my examples are now unnecessary where I have to put the schema in. So I love that feature.
Yeah.
We're getting some, Gilad says that's a good selection. If you could do transactions, semi-structured data and backup and restore, that would be really great.
Okay, so let's start with semi-structured data. So in ClickHouse, you usually have to take care when you create your tables. You have specify the most appropriate data types. Some people, I have seen some people are lazy in this step and just make every column to have string data type. I call it string typing as the opposite of strong typing. And I don't like it because people will lose some of the benefits and performance. They will drop performance from table. Okay, but what if you don't know the types from in advance? What if you have some data set and it is represented by a bunch of JSONs? You can do some research and analyze data types, but you will spend some time for it. Sometimes you have shaky hands because you want to analyze your data as quickly as possible. For this reason, we will have JSON data type, and you can have it for one column in your table, or you can have some columns with predefined data types and the rest with JSON data type. How does it work? What it does? You can insert arbitrary JSONs inside this column. They can be arbitrarily nested. They can contain arrays, multi-dimensional arrays, and so on. And ClickHouse will automatically infer data types on insert. And ClickHouse will unify data types on background merges. So if it was derived by uint 8 in one data part and int 16 in another data type, it will be unified. And what is the most important is that data is stored efficiently in column-oriented format. It's like you get all path from JSONs and store data from every path in a separate column. And you can query this data naturally. Let's look. I have a data set with NBA games. I don't know what does it have. probably it has player numbers, the number of good attacks and so on. But I don't know. I don't want to care. I can store this JSON as a string. It was already available, and it is available today. I can query this data with JSON extract function or with more modern SQL JSON language. I can do it like this. Extract from data. The first key is teams. The second key is one. That means extract from array. And the third is name. It works. And it is processed in half a second. Maybe half a second is good. Maybe it is good, comparable with other database management systems. But for now, I compare ClickHouse with ClickHouse because other systems are way behind and we have to compete with ourselves to optimize our performance. So what will happen if I use the new JSON data type? First, the query will be faster. You see, 15 milliseconds. I'm not good in arithmetic, so I cannot calculate how much it is faster. But also it is more convenient. Compare this and this. This looks like ClickHouse is just a natural database management system for semi-structured data, like MongoDB. You know MongoDB in a good sense. How does it look internally? When you do describe table, you can enable this magic setting to expand the structure, the inferred structure of JSON. And it will look like a tuple of multiple fields. Some fields have deep nesting and represented by multidimensional arrays. Some fields are inferred just as strings. This is fine. So you can have flexible schema in your tables, and you can mix strict and flexible schema in one table. Even if you have flexible schema, queries will work as fast as with strict schema. Sounds like magic. And this is planned for Q1.
Hey, Alexey, we had a
Yes.
really interesting question come up. In fact, there's actually two on semi-structured data. Here it is, semi-structured data and JSON type. We can have thousands of columns in JSON, and I know ClickHouse is not very good with a high number of columns, like lots of memory needed for merges and inserts. Is this still true for the JSON data type?
ClickHouse will combine multiple columns together in data storage. So multiple columns will be stored in the same file. They will still be stored in column-oriented format, but just grouped together. And about memory usage, for merges, it will use vertical merge that will load only one column into memory at once, or not more than a group, a subset of columns. So I expect it will work. But if you have 10,000, 100,000 of columns, it will spend more memory just for metadata, and this problem is not solved. So for thousands of columns, it will be all right. For hundreds of thousands, most likely not.
Okay, a second question, which is from me. so in the current, like right now, I know there's you showed the deficiencies of storing JSON in a string, but one kind of interesting thing you can do is you could stick a Bloom filter on that string. And if you're patient and, tune the index correctly, you can essentially search, do needle in a haystack searches on JSON. And I've seen people do this. It's quite, it's quite interesting, and it actually performs reasonably well. Is it still possible to stick, how do you index, or how do secondary indexes work on these new JSON data types? And can we use Bloom filters across all data in the column?
First, you can create a functional index that will index just one field in this JSON. And you can create many secondary indexes. And if you have array or string field, you can use the same Bloom filter index. But you cannot create this index on top of JSON as a whole. If you want, you can store JSON both as a string and as JSON data type.
Right. Okay, thank you very much.
Okay, let's continue. And the second, the most interesting feature, the most wanted feature of Robert Hodges is support for transactions. So you know that ClickHouse is not transactional database. Why do we need transactions? Why do you want transactions? Because you want to do multiple inserts in atomic way when you insert into multiple tables or tables and materialized views, or even simply multiple partitions of one table. You want transactional semantic for this multiple inserts. And also there is a case when you want to do multiple select queries from the same snapshot. One example is when you have a report, and in this report you have a table and a graph. And you just want to have the same numbers in the table and in the diagram. The user will be disappointed if they will see $5 in a table and $10 on a graph. So we need transactions. And how to explain transactions from technical standpoint? It is quite easy. It is MVCC with logical timestamps. And that's it. The idea is very, very simple, but the implementation is not. And we have more, even more new features to come in 2022. We are almost out of time, but you can select, you can choose one item for me to explain.
We have we are getting some questions about the status of ClickHouse Keeper. I wonder if you could comment on where that stands, and the backup and restore. I think there were a number of us that were interested in how that one's doing.
Okay, so we have time. About the status of ClickHouse Keeper. It is almost production ready. Why I'm saying almost? It is like 99 and 999, and I don't know how to count. The only remaining change that I want before it will be stated as production ready is to ensure that there is no increase in latency during internal hash table resizes. It is pretty minor. It does not, it barely affects anything, but I want it to work perfectly, just perfectly. We already have almost everything. We have all set of functional testing. We have tests with a Jepson framework. By the way, if you know how much it will cost to hire Kyle Silver something. I don't remember his name from Jepson. We will order the validation, independent validation of ClickHouse Keeper, because we're already using Jepson. Also, it is already used in production. For example, in Yandex Cloud for already a few months without any issues. Performance is well optimized in the recent releases. Now it is faster than Zookeeper in reads and writes. It is obviously more memory efficient than Zookeeper. It is obviously more easy to handle, to operate. So almost entirely ready, but not quite. And about backup and restore. We want to integrate backups support directly inside ClickHouse, and we want to make it complete. So you will be able to backup a server with all databases and tables, or a database, or a table, or one partition of a table. And you will be able to do full backups or incremental backups that will reference to previous backup. And you will have a large choice of backup destinations, like local file system, some archive on local file system, or even object storage. This is basically what is yeah. And for restore, there will be full restore and partial restore, and restore with replacing, or restore with adding backup data to existing tables. So plenty of options. It will cover most of scenarios, and I also want this feature.
Okay. We have just a couple of other questions if you have time to take them. Here's a good one. Does ClickHouse Keeper have any advantage over Apache Zookeeper for ClickHouse? I mean, other than the obvious, you don't need to run ClickHouse anymore, or excuse me, you don't need to run Zookeeper anymore.
Yeah, many advantages. First, it fixes many difficulties in operations, even something that can be called like bugs in Zookeeper. For example, in Zookeeper, there is an issue with ZXID overflow. If you don't know what is ZXID overflow, you are happy. And I will not tell you what it is, because I want you to remain happy.
It is true. You will not be happy if your users encounter it.
Yeah, and there are some issues when you have large database with plenty of metadata in Zookeeper, and the size of snapshot is a huge concern. For example, in Yandex Metrica, we have about 15 gigabytes of snapshot size. In ClickHouse Keeper, snapshots will be are already compressed, and the same snapshots compressed 15 times. So it is just one gigabyte instead of 15. I have this rough numbers, but you get the idea. Logs are also compressed, and everything is checksummed. So even if your disks are faulty, it will not introduce any incorrect behavior. Everything will be controlled. And also, one of the most important is memory usage. In Zookeeper, you have to configure the parameters for JVM, and you have to do it right. And sometimes it is not obvious how to do it right. And if you misconfigure, or if you misconfigure, you will have some issues with garbage collection pauses and so on. Sometimes the most important is that you don't have to install some third-party software. What you need is just ClickHouse binary, and it can even run with ClickHouse Keeper integrated in the same process. So you will not have to have separate servers for the Zookeeper. And if you have 3 replicas, you don't have to install 3 more servers for just Zookeeper. You can run ClickHouse Keeper inside the same process.
One practical issue that we've run into as well that you'll solve is people are, if they have Zookeeper, they're tempted to use it for other things than ClickHouse. And then that usually leads to unhappiness. In fact, that often causes the transaction rollover because a bunch of people are updating. So so I think we're kind of running over time here. I want to be mindful of your time because I know it's super late where you are. We did get Kyle Kingsbury, one of our users on YouTube pointed out Kyle Kingsbury is the Jepsen test owner. There was a quick question. When do you think, so when JSON comes out, that's obviously really, or semi-structured comes out, that's a super exciting feature. That'll be experimental when it initially arrives, correct? And when do you think it might become GA? Do you have a sense of that?
We will try to make full coverage by functional tests when this feature is enabled, and full coverage of stress tests and fuzzing if we will make it. And also there will be some production experience, and we will be convinced from this production experience. We will state that it is ready for general production use. So initial release is scheduled for Q1 or early Q2, and I expect it should be ready for production usage in second half of this year.
Okay. Do you want to comment on merge joins? You did mention those, I believe, in the first list. Is there anything like you could say in a sentence about what's happening there?
Yeah. So first, if the joined tables have corresponding ordering with the keys on what you are joining, we should use this ordering. It is just an obvious optimization, and you will wonder why we did not implement it before. But we did not, and we have to keep up and implement it. And second, even if tables are sorted differently, we can sort the data and use external sorting on disk. And this way we can merge arbitrary large tables. There is another algorithm that we have to implement. It can be even more efficient. It is something in between merge and hash joins that is named Grace hash join, or you can name it bucket hash join. Basically, it is to support joining regardless of table sizes.
Great. I want to thank you, Alexey, for joining us. This is really awesome, and it's kind of amazing how many things are changing on ClickHouse and how fast it improves. It is truly amazing. So, and I think I think we all owe you commits, to me included, to help make it better. So with that, I'm going to say I call this meetup closed. Thanks again, Alexey. As just a reminder, there's further details on the clickhouse.com meetup, which is going to be tomorrow. You can hear about 22.2. So there's more meetups coming. And don't forget, if you have something interesting to talk about, please contact me. We'd love to have you on the meetup. We love anything related to databases, but especially ClickHouse. So thanks a bunch, Alexey. Thank you, Pavel. Thank you, Frank. And everybody have a great day.
Thank you for listening. See you tomorrow.
Yeah. Talk to you soon. Bye, everybody.